Welcome back, guys. In this video we're going to discuss a few properties of series and then we will look at some examples where we're determining whether series that involve p-series converge or diverge using what we talked about in the last video with p-series and then adding in those properties of series that we're about to talk about. Then if we have time, we'll do another integral test example so that you've got at least 2 in your notes from the videos. Now, just to review what we talked about in the last video, if you have a p-series like this, it turns out that through the integral test and the nth term test for divergence, we were able to prove that this will diverge when p is less than or equal to 1, and it converges when p is greater than 1. So for example, if I have the sum as n goes from 1 to infinity of 1 over n to the 1.00001, well, p is 1.00001, and that's greater than 1, so the p-series converges. And I love that. I think it's really cool. Remember how we showed that this diverged when p equaled 1? When p equaled 1, we had 1 over x in our integral, and we took the antiderivative to get the natural log of x. And then because of that natural log of x, when we plugged in b, and then we took the limit as b went to infinity, we got natural log of something really large. The whole thing went to infinity. So for our harmonic series, 1 over n, so that's 1 plus 1/2 plus 1/3 plus 1/4 and so on. Oops. This sequence of partial sums was slowly, very, very slowly growing to infinity. So this one diverges. And this is what I think is so cool about this problem. The p-series converges when p is greater than 1, even if it's only tiny bit greater than 1. Even if p is only 0.00001 greater than 1. So I've got 1 plus 1 over 2 to the 1.00001 plus 1 over 3 raised to the 1.00001 plus 1 over 4 raised to the 1.00001. Turns out you add up all of those, and because of that 0.00001, the sum is finite. This converges. Converges to some number, I don't know what it is. This test doesn't tell us what the p-series converges to, but we know it converges. But if that was a 1, if I had 1/2, 1/3, 1/4, so on, diverges. But just slightly larger than 1, and it converges. So there's something very special about that p equals 1, where it switches from growing very, very slowly to not growing that slowly. We're adding fractions that are small enough that they all add together to give us a finite number. I think that's pretty cool. Okay, so that is an example of a p-series. Here's another example of a p-series. Here p is 1/3, so it's the cube root. 1/3 is less than 1. According to this, the p-series diverges. Okay, so now let's look at some properties of series that will allow us to extend what we know about p-series to other series. We also need some exponent properties in this section to extend what we know about p-series to other series. So here are the properties. Let's assume that this series, the sum as n goes from 1 to infinity of a sub n, converges to a. And we'll also assume that the sum as n goes from 1 to infinity of b sub n, a different series, converges to b. So assuming both of these converge, then the following converge. then if I take the sum as n goes from 1 to infinity of c times a sub n, I can factor the c out from all of the a sub n at once. And that's legal because I've got c times a1 plus c times a2 plus c times a3. Just factor them all out. That's c times the quantity, a1 plus a2 plus a3, and so on. C times a sub n, that series, gives us c times the value that this original series converged to. So if this series converges to 10, and I multiply this by 2, the new series converges to 20. It behaves just like you would expect. And if I take the nth term of this series and the nth term of this series, and I add them, turns out I just have to add what they converge to. If a sub n converges to a, if the b sub n series converges to b, the sum converges to a plus b. And if we're subtracting them, I bet you can guess what the conclusion of this is. If this converges to a and this converges to b, this series converges to a minus b. Okay, now this is a big if. We are assuming these two converge. So these statements at the beginning, they're saying they converge to A and they converge to B, but implied there is that they converge to anything. They converge to something. So these series, a sub n and b sub n, both of those series need to converge for the following to be true. In general. Now, if one of those diverges, if this one diverges and that one diverges, we might be able to add them together and get a sum that converges. We might be able to add them together and get a sum that diverges. We might be able to subtract them and get a sum that converges, or excuse me, a difference that converges, or we might get a sum or a difference that diverges. If one of these diverges though, and I multiply it by a constant, taking something that diverges and multiplying it by a constant doesn't change anything. It would still diverge because the partial sums are just going to be exactly the same partial sums with an extra constant attached. You can factor them out, this constant out from the partial sums. So yeah, if the a sub n series diverges, multiplying by a constant, it still diverges. But if both of these diverge, the sum may converge or it may diverge. If both of these diverge, the difference may converge or it may diverge. So there are no guarantees unless they both converge. If they both converge, these properties hold. Okay, keeping that in mind, let's look at some problems involving pSeries. So let's say somebody gives you this. They say, determine whether this series converges or diverges and remember, you're going to go through all of the tests that you know so far. And I'm never going to have you memorize these tests. Well, at least not this semester. I haven't had my students memorize these tests for a while. I'm going to give you a sheet with all of the tests for convergence and divergence on it for your quizzes and tests. But so far we've learned a number of tests for convergence and divergence. We know about telescoping series and when those converge and diverge. We know about geometric series. Those look like this, a constant times a constant to the n. If the absolute value of r is less than 1, these converge, otherwise they diverge. We looked at the nth term test for divergence. If the nth term does not approach 0, the series diverges. If it approaches 0, we know nothing. It doesn't tell us anything at all. Then we've got the integral test. if you can change the n's to x's and the resulting function is positive, continuous, and eventually decreasing, and you want to integrate it because it doesn't look too bad to integrate, use the integral test. And then we also have the pSeries test. P is less than or equal to 1, the series diverges. If P is greater than or equal, or if P is strictly greater than 1, the series converges. So we've got 5 tests now. This is not telescoping. It's not geometric because it's not a constant times a constant to the n. The n's are in the base here. These look like polynomials in n almost, except for that root. The n's aren't in the exponent. When the n's are in the exponent, it's geometric, possibly. But if you've got something that has a lot of polynomials in n, it's not geometric. As n goes to infinity, n cubed grows faster than n squared and square root of n, so the nth term goes to 0, so the nth term test is for divergence is inconclusive. I do not want to change the n's to x's and integrate that, although I could. I just have to check to make sure it's positive, continuous, and decreasing, and that involves derivatives and things like that. I might not want to do that. And the last test is the pSeries test. And this isn't the one that intrigues me when I look at this problem, because this looks like a pSeries. It's not exactly a pSeries, but gosh, it has a similar form to that. I've got some extra constants. I'm adding things together. But if I break this into pieces, I think I can use this up here, provided that the 2 pieces that I break this into converge. We'll also see if one piece converges and the other one diverges, the original series diverges. So let's break this into pieces. Let's make this look like multiples of pSeries added together. So I've got 2 terms up here, so I can break this up into 5 times the square root of n divided by n cubed plus 2n squared over n cubed. That's legal because I've got a monomial in the denominator, so I just take that one and divide by that, and then I take that one and divide by that. We get here. And then we can simplify this. N squared over n cubed, well, that's just a single n. And this is an implied 1/2 power. So we could write that differently as well. It's n to the 1/2 and n to the 3rd. So I can subtract those exponents, and I get n to the negative 2.5. Or just leave it in the denominator, n to the positive 2.5 in the denominator. Now, this is a multiple of a pSeries. And according to this, if I have a pSeries and that pSeries converges, I just multiply by the constant multiple here, like that 5. The original pSeries always had a 1 in the numerator. This one has a 5 in the numerator. That's no big deal. We can factor that out according to this rule. And if the resulting series converges, then this series converges to 5 times whatever that one converged to. So I can factor out the 5, I can factor out the 2. And also, I've got a sum of 2 series. It's not written out here. There's no intermediate step, but this says the sum as n goes from 1 to infinity of a sub n plus b sub n is the sum as n goes from 1 to infinity of a sub n, which happens to be a, plus the sum as n goes from 1 to infinity of b sub n. So I'm going to write out that intermediate step here. Excuse me. And I think if I were to write out that summation, you could regroup the terms so that they were written in this form. Now here's the way this works. If this one converges and this one converges, according to these rules, if both of these converge, the result converges to the sum of the original sums of the series. And then if these both converge, well then these converge to the difference of the sum of the first series minus the sum of the second series. Now, when they diverge, you have to be careful. Okay, so let's talk about this. So I'm looking at this one. You can factor out the 5 if you want to. And I think I do want to. So I've got 5 times the sum as n goes from 1 to infinity of 1 over n to the 2.5 plus 2 times the sum as n goes from 1 to infinity of 1 over n. Well, that's a p-series with p equals 2.5. 2.5 is greater than 1, so this series converges. Now this is a p-series with p equals 1. P equals 1 is less than or equal to 1, so that series diverges. Now here is the deal. It's not listed on our properties over here. Our properties only hold if both of these converge. But this, what I'm about to say, is also true. If this converges, I'm going to add all of these up. I'm going to get a number. Since all these numbers are positive, I'm going to get a number that's positive. So I add these up and I get, let's say 17, and then I take 17 and I multiply it by 5, and then that's the limit of this part, or that's the sum of this part. Now, since these are positive as well, we saw natural log of b in our derivation for this. As b goes to infinity, natural log of b approaches infinity. Since all of these are positive, when I add them up, the sum is infinity. So I've got a number plus 2 times something that's going to infinity. So this sum is going to go to infinity. Since this one diverges, and it diverges in a special way, it diverges to infinity. That means the original series also diverges to infinity. So I'm going to say this original series diverges to infinity. Now if this was approaching infinity and this was approaching infinity, infinity plus infinity, a large number plus a large number is going to be another large number. So I could say the same thing here. If this one converged and this one converged, whether I was adding or subtracting them, this one would converge. Now it's only a little tricky if you have one that's going to infinity and we're subtracting one that's going to infinity. Infinity minus infinity isn't 0. You can't do that. We don't have a rule for that. But if one of these converges and the other one diverges, we can always say that this diverges. Because of the way our partial sums work, we're going to end up with a constant for part of it, and then the rest, if this goes to infinity or negative infinity, this is going to go to infinity or negative infinity. This will dominate the part that's infinite. Okay, so that is one where I used p-series to determine whether a series converged, p-series in algebra. Now let's do another one that's similar, just for practice. Alright, so I've got the cube root of n to the 17th down here. So that's n to the 3, or 17 divided by 3. So that's 5 2/3. But we're not going to write it that way. We're going to leave it this way. And then if you want, you can split this. I've got one monomial in the denominator. It's single term. So do this divided by this minus this divided by this. And then we can subtract. I'll have 3 here. 3 minus 17 thirds. That's 9 thirds minus 17 thirds is negative 8 thirds. Over here, I've got 6 thirds minus 17 thirds. That's negative 11 thirds. And of course, we want to write that with positive exponents, so we'll put the n to the 8 thirds in the denominator here and call that 1 over n to the 11 thirds over here. So I was using a bunch of exponent properties. On this line, we were using the fact that the nth root of x to the m is x to the m over n. That index goes in the denominator. Here, I was using the fact that a minus b over c is equal to a over c minus b over c. That's legal. Remember, back when we learned about fractions, I've got two fractions with different denominators. I subtract the numerators, or excuse me, the same denominators. Like these are the same size parts out of a whole. If I've got a of those parts minus b of those parts, I just subtract the a and the b, and these parts are still all the same size. So the common denominator c is the same. So I use that property here. Then I use this property. If you have x to some power divided by x to some power, it's x to the n minus m. It's the power in the numerator minus the power in the denominator. So I used that. And then I said, okay, if I've got a negative exponent, I could write that as 1 over x to the same exponent but positive. Now you don't have to show this step. A lot of students just go from here to here, and that's fine. But then some students who are really, there are some students that prefer to use this property first and then this property. Okay, now I'm going to break this into two pieces. And I'll factor out the 3, so it looks like I've got a multiple of a p-series over here minus a p-series over here. Here p is 8 thirds. Clearly 8 thirds is greater than 1. So this one converges. Here p is 11 thirds. That's greater than 1, so that converges. This converges and this converges, so the difference converges. So that means the original series that we started with converges. All right. So now let's do one more example of the integral test. Let's say you see a series like this. The sum as n goes from 1 to infinity of 1 over n times natural log of n squared. Now something like this, let's go through our list, all the tests that we know so far. Here's my tests, my list of tests. Is it telescoping? No, I'm not subtracting the same function from itself evaluated at n and n plus k, so no, it's not telescoping. Can I use partial fractions or something like that to rewrite it as telescoping? No, I can't. Geometric? Do I see constants times constants to the nth power, or something that can be manipulated to look like that using exponent properties? No, I got a natural log of n. It's not that. As n goes to infinity, what happens to this? Natural log goes to infinity, n goes to infinity. So this is 1 over something really large, it's really small. So the limit of the nth term is 0, which tells us nothing. So the nth term test does not apply. It's not a p-series. It does look like a p-series, but that natural log of n makes it not a p-series. So the only option here is the integral test. So let's use the integral test for this one. First, I define my function f. And remember how we define f? You just replace all the n's with x's. And that's your function. Actually, we need to start with n equals 2, so we're not taking natural log of 1 in the denominator. I don't want to divide by 0. That'd be bad. Okay, so now this is my f of x, and now I need to check that on the interval starting here and going to infinity, so for x between 2 and infinity, I need to show that this is positive, continuous, and eventually decreasing. I've got to check the requirements of the integral test. Is f positive? We want to know, is f continuous? And is f eventually decreasing? If it is, then we can go ahead and evaluate the integral from 1 to infinity of that, and however that integral behaves is the same way that that series behaves. So you need to check all of these qualifiers. Okay, is f positive? On the interval from 2 to infinity, we always start with the value of the index over here. So we're starting with n equals 2. Well, sure, x is positive for x between 2 and infinity. Natural log of x is positive for x between 2 and infinity. If you're not sure, you should graph it. Here's natural log of x. It crosses at 1. So from 2 to infinity, the y values on the natural log graph, those are all positive. They start from natural log of 2 and they go on up. So yes, the y values on the graph of natural log of x are positive for x between 2 and infinity. And then we're going to square it anyway, so it's definitely going to be positive after we square it. So I've got a positive times a positive. 1 divided by a positive number is a positive number. So f of x, which is a positive over a positive times a positive number squared, is clearly positive on the interval that we're interested in, 2 to infinity. You can say including 2, or not including 2, that would be fine. You could put less than or equal to there if you want. Okay, is f positive? Yes, it is, so we're good to go there. Is f continuous? Sure. Can't divide by 0, so x can't be 0. Well, x equals 0 isn't in our interval. Natural log of x can't be 0. X equals 1. That would be a problem, but n starts at 2, so x equals 1 is not in our interval. So everything is fine here. So f is continuous, yes. Because we're not dividing by 0, we're not taking even roots of negative numbers, we're not taking the logarithm of a negative number or 0 on the interval from 2 to infinity. This function is well defined, and all the functions that we know of that are defined by formulas are well defined on their domains. So we'll say, yeah, f is continuous on 2 to infinity because there is no division by 0, even roots of negative numbers or 0, or even roots of negative numbers, we could take the even root of 0, that'd be fine, or logarithms of negative numbers or 0. Since I don't have any of those things, and we've got a function defined by a formula, this function's well defined and therefore it's continuous. Okay, if it's piecewise, all that goes out the window, but since it's just defined by a single formula, this is good enough for us. And now we need to see if f is eventually decreasing. Well, that means I need to take the derivative of this. You might want to rewrite it first, because you'd have to use the quotient rule, which isn't bad, but then within the quotient rule, you'd have to use the product rule for the denominator. It might be easier to just rewrite it before you take that derivative. To show that f is decreasing, we need to take the derivative and show that the derivative is eventually negative. So let's do that. So we're going to compute f prime. F of x is this. Now we can bring both of those factors up to the numerator. And do that instead, and then use the product rule. According to the product rule we get, if this is my first function and that's my second function, I've got derivative of the first times the second undifferentiated plus derivative of the second times the first undifferentiated. Derivative of the first is negative 2x to the negative 3. Derivative of natural log of x raised to that power requires the chain rule because I've got a function nested inside another function. So the derivative of something to the negative 2, a function to the negative 2, is negative 2 times the function to the negative 3. You bring the power down, then you subtract 1 from the exponent, put the inside function back inside, and then you multiply by the derivative of the inside by the chain rule. And then don't forget that x to the negative 2 from over there. Derivative of natural log of x is 1 over x, or if you prefer, you can call that x to the negative 1. It'll make it simpler to do the algebra in just a second. So we've got negative 2 x to the negative 3 times natural log of x to the negative 2. I have minus 2 x to the negative 1 times x to the negative 2. We add the exponents. That's another x to the negative 3 times natural log of x to the negative 3. Okay, these guys have a lot in common. So they have the negative 2 in common. They have the x to the negative 3 in common. And I've got x to the negative 2 and an x to the negative 3. You could factor out x to the negative 3 or x to the negative 2, either one. I'm going to factor out x to the negative, or the natural log of x to the negative 3, because what's left over here won't have negative exponents, and that'll be nice. And we'll rewrite all of this so it doesn't have a negative exponent anymore. So I'm going to ask myself, in order to factor this times what, or times what here, will give me this. We've already got that and that. In order to get a natural log of x to the negative 2, we need natural log of x to the positive 1. Because natural log of x to this power times natural log of x to that power, if I add the exponents, that's natural log of x to the negative 1 plus, or negative 3 plus 1, which is negative 2. So that's right there. Then I say to myself, this times what gives me this? I think it's just a positive 1. Okay, so this is our derivative. Going to write it a little differently now. I've got a negative 2 here, x cubed there, natural log of x cubed in the denominator, and then I have this 1 plus natural log of x over here as a separate factor in the numerator. So this is our derivative, and in order to determine whether this derivative is negative eventually on that last interval that includes infinity, I need to figure out where it's 0 and then find out where the last interval actually starts. So we compute f prime, and you set f prime equal to 0 like you're doing the first derivative test in Calc 1. Now the only way this fraction is 0 is if the numerator is 0, because 0 divided by anything is going to be 0. Or if you prefer, you can multiply both sides by the denominator, and that's just going to reduce, and you're just going to get the numerator equals 0. And negative 2 times something equals 0 if that something equals 0. Or if you prefer, you can divide both sides by negative 2 and you get the same thing. Subtract 1 from both sides. To get rid of the natural log, say e to this power equals e to that power. Logs and e's are with the same base undo each other. So x is e to the negative 1, or 1 over e. And actually we're on the interval from 2 to infinity, so that's actually less than 2. So f prime is equal to 0 at 1 over e. But we're really just interested in what happens after x equals 2. Now remember where that comes from. That comes from right here. We start at x equals 2 because it's where n starts. Okay. For x greater than 2, greater than or equal to 2, what happens to this? Let's look at all the factors separately. I've got a negative 2, 1 plus natural log of x, x cubed, and natural log of x cubed. And remember how the natural log looks. This is y equals natural log of x, and here's x equals 2. We're over here. So the y values on the natural log graph when x is greater than 2 are all positive. They're actually all greater than natural log of 2. So if I take that number and I cube it, I'm going to get a number that's positive. And if x is greater than 2, x cubed is greater than 8, so that's positive. Now, natural log of x plus 1, well, natural log of 2 is positive, then I add 1 to it, it's still positive. And then this negative 2, that was in the numerator right here, that's going to stay negative the whole time. So this is a negative times a positive divided by a positive times a positive. So a negative times a positive is a negative, divided by a positive is a negative. So that's good. So what did we just find? We set f prime equal to 0, then we created a sign chart. And we're trying to find the sign of f prime on that last interval, the one that goes from some x value to infinity. Since f prime is negative, that means the slope is negative over there. And if the slope is negative, that means the function is decreasing. A lot of work to use the integral test. You have all these conditions to check. That's why I usually use different tests. But it's a nice test and it gave us pSeries, so we're grateful for that. So this shows us that f prime is negative for x between 2 and infinity. If the derivative is negative, that means f is decreasing on that interval. Decreasing. Okay. So what did we find? F is positive, continuous, and eventually decreasing. It sure is. So now I can use the integral test. See, a lot of work just to get to this point. So the integral test says, evaluate this integral. However, this integral behaves the same way the series behaves. If this converges, the series converges. If this diverges, the series diverges. Okay. So first we write down the improper integral and then we rewrite it as a limit. Upper limit is infinity, so we replace that upper limit with a b and let b go to infinity. So we always write the improper integral as a proper integral. That's the first thing we do. And then, whenever evaluating improper integrals, we evaluate the proper integral using the fundamental theorem, because the fundamental theorem applies to this, but it did not apply to this. So we go ahead and use the fundamental theorem here. So I guess I should be using equals, not implies. This is the limit as b goes to infinity of this guy. I'm just going to rewrite it. And this integral can be evaluated using a u substitution. Now remember, we always use our basic rules first if we can, and if basic rules fail us, always try USub. Now whenever you're using USub, you're looking for a function nested inside another function. I see that natural log of x in parentheses, and I'm thinking USub. That's probably my u. Now I don't know that this will work until I take the derivative of u and see if the derivative of u, du, is up there as a factor. So I need that derivative times dx, and possibly times a constant. Derivative of natural log of x is 1 over x multiplied by dx, and we've got a factor of 1 over x dx, so this is going to work just fine. Now I need new limits of integration. So I evaluate u at the original limits of integration. So we substitute in b here and here. We substitute in 1 here and here. And remember, natural log of 1 is 0. So this limit is the same as this limit. 1 over x dx is du. That together makes a du. And here I've got a u squared, but it's in the denominator. And now I need new bounds. My lower bound used to be 1, now my lower bound is 0. My upper bound used to be b, now my upper bound is natural log of b. And so we evaluate the integral of this. Now be careful, the integral of this is not natural log of u squared. If that exponent is anything other than a 1, the antiderivative is not natural log of the denominator. In this case, you've got to rewrite it, bring that u up to the numerator, make that a -2 power, and use the power rule. So we add 1 to the exponent, divide by the new exponent, plug in u equals 0, and plug in u equals b and subtract. Uh-oh. Oh, I see what the problem is. See what I did? N started at 2, not 1. So that's got to be a 2. That's going to be better. 2 here, 2 here, 2 here. So that's not a 0. So this should be a natural log of 2. Sorry, guys. If I plug in 0 to this, I'm going to have a problem. I'd be dividing by 0. Okay. But because we wrote this series to start at n equals 2, we don't have that problem. So we're plugging in 2 for x, which means we've got natural log of 2 for b, or natural log of 2 for u. Okay, so this is a -1 times u to the -1, which is the same as 1 over u. And we're evaluating this from u equals natural log of b to u equals natural log of 2, or I think I said it backwards, the other way around. We plug in the upper limit and the lower limit and we subtract. The upper limit, we get this. When you evaluate this at the lower limit, you're subtracting a negative, so that means you're adding this. As b goes to infinity, natural log of b slowly goes to infinity, so 1 over something really large eventually is going to be really small. Hey! So our improper integral converges. That's cool. What were we doing again? What was this question about? Was this an improper integral problem? Yes and no, right? This was an integral test problem. The question was not about that integral, but it was about this series. And remember what the integral test says. If this integral converges, then this series converges. Now, the integral happened to converge to 1 over natural log of 2. It doesn't tell us anything about what the series converges to. All we know is that if this converges to something, that the series converges to something as well. Not the same something. So, since this converges, we can say, we're absolutely sure, according to the integral test, that this converges by the integral test. We see that the integral test, it's a good test, it works. It's a little long and involved. It takes a lot of work to show that it's positive and continuous, and then eventually decreasing was all of this. It was a full page of work. But once we were able to do that, all we had to do was evaluate this improper integral And once we were able to do that, since the integral converged, we could tell that the series converged. Okay, so let's recap. You've got 5 tests. You've got telescoping series. You've got geometric series. Telescoping series have this form. So you've got a function of n and a function of n plus k, and you're subtracting them. And it could be in the reverse order. But if one term is positive, the other term is negative. After some cancellations, the partial sums are going to have a finite number of terms. That's what makes it telescoping. For these, we can find S sub n, and we compute the limit as n goes to infinity of S sub n to determine the sum of the series. Geometric series look like this. We've got a constant times a constant to the n. This constant r is called the common ratio. With this, you just look at the common ratio. Once you've written it in this form or identified that you're always multiplying by the same thing to get from term to term. Once you've identified that number, that thing that you're multiplying by to get from term to term, the common ratio, if the absolute value of that number is less than 1, the series converges. If the absolute value of that number is greater than or equal to 1, the series diverges. And then we learned the nth term test. This said, if you've got a series involving a sub n is your nth term, if the limit as n goes to infinity of a sub n is not 0, the series diverges. It also says if the limit as n goes to infinity of a sub n is 0, try something else. The test is inconclusive. You can't be sure that the series either converges or diverges at that point. Okay, so that's that. Then we learned the integral test. This was the most involved of all the tests. It said, look at this series, or look at this integral, and then look at this series. If you have a bunch of properties that hold, if f is positive, continuous, and eventually decreasing, the series and the improper integral have the same behavior. So you just show this part, and then you evaluate this integral. If this converges, this converges. If this diverges, that diverges. That's a lot of work, but we're grateful for the integral test because there are some cases when it works quite nicely, especially if nothing else works, especially if our series is not telescoping, geometric, and the nth term test does not apply. But why I'm really grateful for the integral test is because the integral test gave us this gift of the pSeries test. The pSeries comes up a lot. pSeries and geometric series are going to come up a lot in the rest of this chapter. pSeries have this form, or you can multiply them by a constant. Sometimes people call those constant multiples pSeries as well. So these two guys are really important. They come up a lot. So this is a constant times a constant to the n. The n's are in the exponent. Here, you've got n to some power. The n's are in the base. So these look like polynomials in n. These look like exponential functions. With the integral test and the nth term test for divergence, we were able to prove that if p is less than or equal to 1, the pSeries diverges. And if p is greater than 1, strictly greater than 1, the pSeries converges. That's what happens. So now you've got all of these, but these are our go-to tests. They're the easiest. If I can just look at r, absolute value of r is less than 1, get an answer. Absolute value of r is greater than 1, get an answer. If I can look at p See if p is less than 1, less than or equal to 1, get an answer. See if p is greater than 1 and get an answer. Those are going to be our go-to tests. But if it's telescoping, that's nice. We can find the sum of the series. If the nth term test applies, the limit of this guy is not 0. We know immediately it diverges because this is called the nth term test for divergence for a reason. It never tells you whether something converges. It just tells you if something diverges. The series diverges, excuse me. And then the integral test. It's a very powerful test that requires a lot of work. We have to check all of these things. But if we check these things and they check out, this integral and this series have the same behavior. The improper integral, when it converges, this series converges. When the improper integral diverges, the series diverges. Okay, so that's it. That's our review. That's it for integral test. We're going to build on all of this next week, and we're going to learn more tests. So make sure you learn these 5 tests. Make sure you learn them really well, and you know when they apply, which circumstances. This sheet that I've given you so far is a great summary, and there's also the sheet of tests for convergence and divergence of series online on the website.